Vinton Cerf currently serves as Vice President and Chief Internet Evangelist at Google. He is a noted industry luminary, probably best known for his work with Robert Kahn in designing the TCP/IP protocol and for playing a key role in leading the development of Internet-related data packet and security technologies. I am privileged to speak with Vint and get his perspectives on the many decades since the initial work at the dawn of the Internet, the challenges facing us today, and what innovation will mean for the future. Vint, thank you for joining us.
It's a pleasure to be here, Kevin.
I'd like to just start with your perspective. When the first packet switch network was formed as part of ARPANET, what was it like in that day, and how did that innovation come together with the team of people that worked on it?
Well, the network was actually started, effort was started by Larry Roberts, who was brought down from Lincoln Laboratories to DARPA to lead this development of a packet switch net. The contract went to a company called Bolt, Beranek and Newman in Cambridge, Massachusetts, and among the people there, Bob Kahn served as one of the key architects. So Bob came out to visit UCLA, where the first node of the ARPANET was installed in September of 1969. And I was a graduate student at UCLA at the time, responsible for connecting the host up to the IMP, the Interface Message Processor. Leonard Kleinrock was running what was called the Network Measurement Center. And my job was to write the software to figure out whether or not the network would behave and perform in the way that Len Kleinrock's queuing theoretic models predicted. So Bob came out to go kick the tires, so to speak, after 4 nodes of the network had been put together somewhere around December of 1969. It was pretty early days when you think about it. The data rate that we could sustain on the telephone lines linking the interface message processors was 50 kilobits per second. So there were things that we could not do then that we do today with similar packet switch technology.
Well, certainly things have evolved since then. Did you feel, you and the team working on this, when you first got those 2 or 4 nodes communicating and working together, did it dawn on you what that might turn into at that point in time?
Well, certainly in the earliest stages, I don't think we had any idea what was going to come out of all this. However, there were things going on with time-shared machines that gave some hint of what was to come. Time-sharing had been invented by MIT, particularly I think of John McCarthy and Marvin Minsky, in the early 1960s. So all the machines that were put up on the ARPANET were in fact time-shared machines. They could theoretically be accessed remotely. So the ability of people to get access to resources that were not local was a very important motivation.
So that'd start to create demand for using this network.
Exactly, exactly. This idea that you could share somebody else's results was really important.
You describe a lot of concepts, even beyond networking, that have evolved into the technology that has become ubiquitous today.
One of the fundamental ideas behind packet switching is sharing of resources, particularly sharing of large quantities of resources. The law of large numbers is helping us there. The other thing that was very interesting is that the layering idea was very quickly instantiated both in the ARPANET protocols and then subsequent Internet protocols. And the layering had the nice property that the packets didn't really care exactly how they were being carried. So the medium was irrelevant, satellite, radio, optical fiber. And they also didn't know what they were carrying. So it was just a bag of bits. And the power of that end-to-end notion was that the bits didn't mean anything to the network. It only meant something to the software at the edges of the net. And that's probably the primary engine that's driven innovation in the Internet, has been the fact that the net doesn't care what the applications are.
So at a very early stage, the view that this horizontal approach of based on standards, so that software on each end could just sort through those protocols. So is that sort of the foundation for TCP/IP?
It's certainly that, and the predecessor protocols on the ARPANET were similarly standardized for all the machines. In fact, it was a demonstration that multiple operating systems could safely exchange information despite the fact that they had different word sizes and different specifics in the operating system environment.
Then you look at how that technology has had an impact on the world, and you look over the last decade or the last 2 decades, and certainly how the Internet went through a phase of sort of in academia and government, and then became something that consumers start to use. And Share with me kind of your view. Have there been certain milestones or stages when you look at that whole evolution that you've observed or you think are critical?
Some that really stick in my mind. Apart from the earliest days of getting the ARPANET to work, there was a big demonstration of ARPANET in October '72 in Washington, D.C. To the public. It was the International Conference on Computer Communication. So that was probably the biggest visible evidence that packet switching would work, and it could work in a real-time interactive way. Then Bob Kahn and I started working on the internet design, and that evolved over time. We had a full definition of the TCP protocol by December of 1974. 1977 really sticks out in my mind. It was November 22nd, 1977. I'm now at DARPA along with Bob Kahn. And we have 3 packet switch nets that are around. There's the Bay Area mobile radio packet radio net. There's an Atlantic satellite network linking the U.S. with Europe, Norway, and London in particular. And then there's the ARPANET, which by this time has grown pretty dramatically. So for the first time on November 22nd, we got all 3 of those different networks to interact with each other. That was a very big milestone.
Well, certainly the explosion of traffic driven by, this proliferation of devices and access points, the increase in video, and even machine-to-machine communications all using that network is putting a lot of pressure on traffic per subscriber, if you will. Your thoughts on things like machine-to-machine? I mean, people see video traffic increasing, but certainly with cloud-based computing and as more data is now held in these mega data center, things like the smart grid, do you see that as being an additional driver of traffic?
So that's interesting, because on the smart grid side and more generally devices, sensor devices and things like that, I don't see that as a huge driver. The numbers are big, but the amount of data that has to be moved back and forth is really quite modest. So I don't anticipate huge amounts of data traffic there, smart grid similarly. On the other hand, the cloud computing environments, certainly the ones that we're familiar with at Google, do involve massive amounts of data motion back and forth within, today, a private network that links all of our data centers together. Each of them is then connected in turn to the public internet. But we haven't yet experienced in our internet world is the data center to data center or cloud to cloud interaction through the public internet. And here I think you're right to draw, highlight that particular issue, because I'm anticipating that a substantial amount of data is going to have to move back and forth between clouds, because users are going to want to have the flexibility to put their data wherever they want, or maybe cause joint computations to occur between clouds. So the cloud world, or intercloud world, is today, in 2009, where the internet architecture was in 1973.